Now I also kind of want to break this up and make it a little bit simpler. When it comes to figuring out this number of electrons transferred, students can get a little confused by it. So what you're going to measure is the slope. So you're going to have your voltage versus L and Q, and you're going to have the voltage going up for the copper plus 2, and you're going to have the voltage going down for the zinc plus 2. And this is just Le Chatelier's principle. As we start adding more zinc plus 2, we're actually on the wrong side of the reaction. We're adding products, so the reaction becomes less favorable, so the voltage goes down. When it comes to the copper plus 2, as we start adding more copper, that's a reaction. We drive the forward reaction, which makes it more favorable, so we expect a positive slope. But in both cases, the slope here, the absolute value of the slope, so let's call this slope 1, slope 2, the absolute value of both slopes is equal to RT over NF. Now R here is your ideal gas constant, 0.008314 kilojoules per mole Kelvin. Temperature here is going to be whatever temperature you take the measurement at, so it's going to be, keep in mind, got R in there, so it's got to be in Kelvin. F here is Faraday's constant. F is 96.485. And in here is your number of electrons. So to figure out the number of electrons transferred, move N over, move your slope over, we get the number of electrons transferred is just RT over the absolute value of the slope times Faraday's constant. Now, N is a very unreliable number in this measurement. And the reason why it's a very unreliable number is that if we look at ln of Q, it doesn't span a lot. Typically we're going from like 0.1 to maybe 1. Ideally we would span what's called multiple decades. So 1, 0.1, 0.01, 0.001, and that would give us a lot better feel for the slope. But because of just practical limitation, the sensitivity of most voltmeters, we can only go from 1 to 0.1, so we expect to have very, very poor answers in terms of the number of electrons transferred. We know it should be 2, but it's very likely we're not going to get 2. The reference potential, though, we're actually expecting that to get that pretty well, because we're actually going to measure it. Where you have the concentration of zinc and copper both is 1 molar, that's where that cell potential comes from, that E0 cell. So we're actually going to be measuring that directly, and because we're so close to the reference potential and we don't expect to get far away from that reference potential because of how small this Q range is, we're actually going to get pretty good numbers regarding the reference potential. So keep that in mind when you do this calculation. Your cell potential should actually be really close to what it should be theoretically. But don't be surprised if your number of electrons goes as low as 1 or as high as 3, just because we're not really spanning a very big range of ln of Q.